Hi everyone, in this video we'll be looking at level annuities where cash flows are paid continuously as well as pthly. If you haven't seen my video on discrete level annuities, have a look at the link above or in the description below. So we've seen the relationship between nominal and effective interest rates and nominal and effective discount rates before, shown using these formulae. We have also seen the accumulation and discount factors that we use when we have a force of interest, more specifically when our force of interest is constant. We also know the relationship between our rate of discount and interest rate and discount factor. A continuously payable annuity is one where our cash flows are paid continuously at a rate pt per unit of time over the period from time 0 to time n. This is different to our discrete level annuities where cash flows are then paid at discrete times. Here cash flows are paid continuously. Assuming a force of interest that is non-zero, we can calculate the present value by discounting our payment function using a discount factor. Here our payment function is 1 per unit of time, and using the simple rules of integration, we can calculate the present value as follows. This formula for the present value is denoted using this annuity function where our force of interest is non-zero. We can use Vn since our force of interest is constant. If our force of interest was 0, we would have the present value of this annuity equal to n. More formally, we have the present value of an annuity payable continuously between time 0 and n, where n is greater than 0, where the rate of payment per unit of time is constant and equal to 1, as follows. We can also show our continuously payable annuity in terms of our discrete level annuity by multiplying it by this factor. Here we have pulled out the constant force of interest and we've multiplied by I, where the I cancels out below. This can be useful since the discrete level annuity values are found in the tables. In order to calculate the future value of a continuously payable annuity, we simply accumulate the cash flow function for the period of time. The simple rules of integration show us thus that this is simply accumulating the present value of the annuity function for the time period n. More formally, we can see that the future value of an annuity payable continuously between time 0 and n, where our rate of payment is constant, is as follows. Here we simply multiplied our present value of the continuously payable annuity function by 1 plus I to the power n. In a similar way, we can show a continuously payable annuity accumulation in terms of the equivalent for a level discrete accumulation, and these values are also found in the tables. We know how to calculate the present value of a level annuity of 1 that's either paid in advance or in arrears for n periods at an effective interest rate per period of I. Now we want to consider calculating the present value of an annuity where payments are made p times per year for n years. In other words, we will have n times p payments in total. If we draw a timeline to flesh out what these payments are and at what time points they're paid, we can see that payments are made at time 1 over p, 2 over p, all the way to time n. Each of these payments are 1 over p in amount. Now, if we've got n times p payments in total, and each of these payments are 1 over p, then the sum total, if we had to add up all of these payments, it'll add up to n. So here we've got n times p payments in total, and if we sum up all the payments, we will have a value of n. Now we need to consider different scenarios. We are familiar with the case where p is an integer. This is where we take a period of a year and we split it up into either half years, quarters, or monthly, and we're familiar with that concept. And we also understand where our period or our time period is n years, where n is an integer. 2 years, 3 years, 4 years, 5 years. We've got two other cases where our p is a fraction between 0 and 1, and where n is a positive non-integer, in other words a positive fraction, where n is an integer multiple of 1 over p. This is an important condition, and we will look at this a bit more closely in the slides to follow. First, we look at the case where we have p as an integer and n as an integer. Let's start with the present value of an annuity payable p times per year in arrears for n years. If we had to draw out this timeline, we can see that the first payment is made at time 1 over p, since payments are made in arrears, and the last payment is made at time n. What we're trying to do now is discount each of these cash flows to time 0 to calculate the present value. We can write out our equation of value to calculate the present value by discounting each of the cash flow payments. Our first period is 1 over p, so we discount it over 1 over p. Here v is our discount factor that uses an interest rate of I% effective. This is an effective interest rate per annum. We then pull out a common factor of 1 over p, and we call the terms in the brackets a. Now the trick to use is to first write out what a is and call this line 1, and then we take a and multiply it by 1 plus I to the power 1 over p. This gives us a new series that starts with 1 and ends with v to the n minus 1 over p. Let's call this line 2. Now the idea is then to take line 2 and subtract line 1 from it. The terms will cancel out and you are left with 1 minus vn. But on the left hand side of your equation, you will have a times 1 plus I to the power 1 over p minus a. And if you pull out a as a common factor and you move everything to the other side such that you have a on the left hand side, you end up with 1 minus vn over 1 plus I to the power 1 over p minus 1. Now the next step is to simplify this into something that we know. So we'll be using our relationship between nominal and effective interest rates to substitute into our equation for a. What we'll try and do is get 1 plus I over 1 over p minus 1 on one side of the equation and see what we're left with. We will then replace this value in our equation for a. This leaves us with 1 minus vn over ip over p. We then look back at what is our present value. Our present value formula was 1 over p times a. The p's cancels out and we're left with 1 minus vn over ip. This is our annuity, a present value of an annuity formula where our cash flows are paid p times per year for n years and cash flows are paid in arrears. More formally, the equation can be written as follows, where we are calculating the present value of an annuity payable pthly in arrears for n years. An important thing to note here is our assumption for p. P must be an integer greater than 1 and n must be an integer greater than 1. That's what we've used and shown so far. We will build on this and show in which other cases and under what other assumptions you can also use this formula. Here we keep the same assumptions for our p and n, both as integers greater than 1, and we now look at the present value of an annuity where cash flows are paid p times a year but in advance. We see that the first cash flow is paid at time 0 and the last cash flow is paid at n minus 1 over p. Our term here is still n years and cash flows are still paid p times per annum. We now need to discount them in the same way that we've done before. We write out our equation of value. This time we pull out the common factor up front. We're still using v, where v is 1 over 1 plus I and I is an effective rate per annum. We then call these terms in the brackets b, and we write this out as line number 1. The trick now is to take b and multiply it by v to the power 1 over p. This gives us the following terms that start with v over 1 over p all the way to vn. Let's call this line 2. We then take line 1 and subtract 2 from it, and this gives us 1 minus vn as the common terms cancel out. On the left hand side, we're left with b times 1 minus v over 1 over p. And to get b on the left hand side only, we move the term in the brackets across, and we're left with b equal to 1 minus vn over 1 minus v to the power 1 over p. We now need to simplify this into something that we know. Over here, we're trying to replace the denominator. So we start with v is equal to 1 minus d, and we try and find out what v to the power 1 over p is equal to. And we get 1 minus d to the power 1 over p. We then use our relationship between nominal discount rates and effective discount rates in order to calculate what 1 minus d to the power 1 over p is, and then we simply take it across and we end up with 1 minus d over 1 over p is equal to dp over p. We then can combine these two and replace the denominator in b using dp over p. Substituting that in for the denominator and looking back at what our present value is, we see that the p's cancel out and we're left with a present value formula equal to 1 minus vn over dp, and this is the present value of an annuity where cash flows are paid p times a year in advance for n years. More formally, we can see that the present value of an annuity payable pthly in advance for n years is as follows, assuming that p is an integer greater than 1 and n is an integer greater than 1. Like I said before, we are building on these definitions, and by the end of the video you will have a clear understanding of when you can use this and when you can't. So far we've looked at the case where p is an integer and n is an integer, so we've done 1 and 1. Now we're going to look at 1 and 2, the case where n is a non-integer but where n is still an integer multiple of 1 over p. This is best explained using an example. Now in this case, we want to calculate the present value of an annuity of 1 payable quarterly in arrears where there are 42 payments. So we know that p is equal to 4, that satisfies our first condition, and we are told that there are 42 payments. So we're not told directly what n is, but we can work back using the fact that n times p is equal to the number of payments. Here we see that n is equal to 10.5. This is a positive non-integer. But now we need to assess if n is an integer multiple of 1 over p. And to do this, we need to test if n times p is an integer. We know that n times p here is equal to 42, which is an integer, and therefore we've satisfied the conditions for number 2, where n is a non-integer, but is also an integer multiple of 1 over p. Now that these conditions are met, what does this mean? It means that we can calculate the present value using our usual pthly annuity formula. In this case, we can use this one where we have 4 payments per year for 10.5 years, where payments are made in arrears. So the idea is, if you meet these conditions, you can use the usual annuity formulas. Let's look at another example. Here we have an annuity of 1 payable biannually in arrears. So we know that p is equal to 2, that satisfies the first condition. And we've got n equal to 10.25. This is a non-integer, but is it an integer multiple of 1 over p? We need to test. So looking at np, we see that np is a non-integer, in which case n is not an integer multiple of 1 over p, and this means we cannot use our pthly annuity formulas. What do we do instead? So in the case where n is not an integer multiple of 1 over p, we need to split up n into 2 parts such that we have one part that is an integer multiple of 1 over p and the other that is not. So in this case, f is not an integer multiple of p, and it lies between 0 and 1 over p. Then in our example where p is equal to 2 and n is equal to 10.25, we can split up n as 10 plus 0.25. This means all the payments over the 10 years need to add up to 10, and the one payment that's left needs to add up to 0.25. So since p is equal to 2, we can see that for the first 10 years, we will have 20 payments of 1/2 each, such that if we add up all those payments, we end up with 10. And then we have one payment made at the end of the period, since payments are made in arrears, and this payment is equal to 0.25, and it's made at time 10.25. This means we can use our usual annuity formulas for the first 10 years since n times p is an integer in this case, and we will then simply discount the last payment as a single payment on its own. And that's how we treat this case. More formally, if we have a case where n is not an integer multiple of 1 over p, then we have that n is a non-integer but not an integer multiple of 1 over p, and we will split it up into two components where n1 is an integer multiple of 1 over p and f is not an integer multiple of 1 over p, but f lies between 0 and 1 over p, and we have this genetic formula for calculating the present value. Please note in this case p is still an integer greater than 1, and this specifically deals with an annuity that's paid in arrears. So we've seen the case where p is a positive integer and n is an integer, as well as the case when n is a non-integer, and as long as n is a non-integer that's also an integer multiple of 1 over p, we can make use of our annuity formulas. Now let's look at the case where p is a value between 0 and 1, i.e. a fraction. When we have p between 0 and 1, we need to check if n is an integer multiple of 1 over p. So whatever n is, if it's an integer or a non-integer, we just need to make sure that it's an integer multiple of 1 over p. If it is, we can use our normal pthly annuity formulas. If it's not, we then need to split out our n between a component that is an integer multiple and a component that is not, and we would typically write out our present value like this. This example is looking at where we have cash flows that are paid in arrears. So we've seen how to calculate the present value of annuities payable pthly. What about accumulating annuities payable pthly? Well, instead of deriving it from scratch, we can look at what we already know. We already know if you've got cash flows paid in arrear, we can easily calculate the present value using the annuity formula for this. And if you wanted to know what the accumulated value of the same cash flows are at time n, we can simply accumulate our annuity formula for n years using 1 plus I to the power n. This gives us the future value or the accumulated value of these cash flows at time n. And if we look at how the formula looks, we can multiply the 1 plus I to the power n right through to simplify this formula. And if we do this, we get a formula for the accumulated value of an annuity payable pthly as follows. We can do the same thing for an annuity that's paid in advance by multiplying the present value of the annuity formula by 1 plus I to the power n. This gives us 1 plus I to the power n minus 1 over dp. All of these apply for when our interest rate is greater than 0. More formally, we have the future value of an annuity payable pthly in arrears for n years as follows. And remember, this is when we have p as an integer or n as an integer, or when n is a non-integer as well as an integer multiple of 1 over p. So this is the case when we want to work out the future value of an annuity payable where the payments are made in advance for n years. Note again, here we need p to be an integer greater than 1, or n as an integer greater than 1, or n as a non-integer where it's still an integer multiple of 1 over p, or if we have p that's between 0 and 1, as long as n in this case is an integer multiple of p, we can use this formula. So wrapping things up, looking at our key takeaways, we've got a formula to calculate the present value of an annuity payable continuously, and we can also work out the future value of the annuity payable continuously. Here we are using a constant force of interest denoted by delta. So to summarize what we've learned about calculating the present value of an annuity payable pthly for n years, we've got two formulas that we can use for where cash flows are made in arrears or in advance, but we first need to assess if the assumptions hold. Where we have p that's an integer greater than 1, or p that's between 0 and 1, we can use it with any n as long as n is an integer multiple of 1 over p. So it's important to test whether n is an integer multiple of 1 over p, and we do this by checking if n times p is an integer. If these conditions are met and satisfied, we can use these formulae. When we're calculating the future value of an annuity payable pthly, we can use these two formulas for when cash flows are made in arrears and where cash flows are made in advance. Again, we need to use and check the same assumptions in order to use these formulae. For when we have annuity that is paid in arrears and n is not an integer multiple of 1 over p, then we need to split up our n into a component that is an integer multiple of 1 over p and f a component that is not an integer multiple of 1 over p, where f lies between 0 and 1 over p. In this case, we can calculate the present value of this annuity that's paid in arrears using this formula. All we've essentially done is we've split out the component that can be used with our annuity function and a component that cannot be used. This is a case for when we have cash flows in arrears. We can then find the future value by simply accumulating the present value. This only applies for when we have cash flows in arrears. You can work out an equivalent for when you have cash flows in advance. As a top tip, always remember to use your timelines, especially when you're working with pthly annuities, because it is very difficult to visualize them otherwise, as there can be several made in a single year, and catching the end date is also important to determine which annuity function you use, especially in the case where your n is not an integer multiple of 1 over p and where you are needing to split out your n into two components. And that's the end of this video. If you enjoyed the video, please like, subscribe, and share it with your friends.